Okay, we're going to talk about growth and decay. We've already talked a little bit about growth and decay. Most of you should already know at this point that if you have something going, or an exponential graph going in this direction, you're dealing with growth. If you have an exponential graph going in this direction, excuse me, not that, this direction, you're dealing with decay. Okay, that's what you already know. Alright, but there's actually an exponential form or equation for growth or decay, and that is y equals c times 1 plus r to the t power. And down here, it gives you all the information that you need in order to fill in those blanks. So y is the initial amount, c is the initial amount, y is the final amount, c is the initial amount, the starting amount, r is the rate of change. We got to take that, usually it's a percentage, we got to take that and put it into decimal form, and then t is time. Oh, by the way, we're about a minute into the video, but I wanted to let you know you can print these notes off of Blackboard before you watch them. Okay, so you can fill these in as you go. So make sure you print these notes. Alright. And if you need to, I guess pause and go back and print the notes. So let's just go ahead and get right into it. Look at example 1 so we can get through this as quick as possible. Example 1, it says in the population in 2005 of Flat Creek had a population of about 280,000 people and a growth rate of 0.85% per year. So our first thing to do is to write an equation that represents the population of Flat Creek since 2005. So what I need to do is just fill in what I know. Again, my general equation is y equals c times 1 plus r to t power. So if I fill in what I know, okay, I don't know y, so y equals c is my initial amount, and my initial amount based on the problem is 280,000. Okay, times 1 plus r, which is my rate of change in decimal form. So my rate of change is right here at 0.85%. If I take 0.85% and change that from a percent to a decimal, I move my decimal place 2 spots to the left. So 1, 2. That gives me 0.0085%. So I have 1 plus 0.0085 raised to the t power, and again, t is time, and in this particular point, we don't know what the time is. So when I do these, I want to go ahead and simplify. Okay, so I want to simplify right here in the parentheses. So I have my actual final answer is y equals 280,000 times 1.0085 to the t power. And right there would be my final answer. Okay, the next part of this says, according to the equation, what will be the population of Flat Creek in the year 2015? So the time then is going to turn from t. Now I'm going to take the same equation, y equals 280,000 times 1.000, sorry, not 85, and instead of t now, I know that t equals 10 years because we're talking about a time frame from 2005, from the initial equation, 2005, to now we're talking about 2015. So that's 10 years. So t is now 10, so I'm going to put that up in my equation, and then I'm going to work it out. So y equals 1.0085 to the 10th power is roughly 1.088. So y equals 280,000 times 1.088. So y equals about 304,731. And I could round that to the nearest tenth and it'd be like 0.3 or something like that. But this would be my answer. Okay, at this point, really all I'm doing is I'm taking that exponential growth or decay form, a formula or equation or whatever, and then I am plugging in what I know. Okay, so now let's move on to our next example. Example 2 says a population of 400 sea otters decreases. Okay, so again, we need to kind of get into the test-taking strategy, the EOC test-taking strategy, and we see the word decreases. That should tell us that's going to change our problem just a little bit. Decreases means subtracts or declines. So a population of 400 sea otters decreased by 2.5% per year. Which of these functions can be used to determine the number of sea otters Y in this population at the end of T years? Okay. Again, we're using the same formula. Y equals C times 1 plus R to the T power. That's our initial formula that we start off with. Now we got to make some changes to it. Okay. What do we know? Well, we definitely don't know Y because it's asking us what Y is. So Y equals. What is our initial amount? Well, our starting amount was the 400 sea otters. Okay, so that's going to be our C value. So C equals 400. Okay, times 1. Now, let's look at here. This word decreases means that we're going to change this sign here, this positive sign, from a positive to a negative. So it's going to be 400 times 1 minus now instead of plus. And then our rate is 2.5%. But again, we need to move our decimal 2 places to the left. So when I do that, I do 1. I'll move it over to the left 2 spots, 1, 2, and I end up with 0.025. So my rate equals 0.025. And not percent anymore because I put it into a decimal. So I do 1. So now I have Y equals 400 times 1 minus 0.025 to the T power. Okay. This should be our answer, and if we did everything correctly, because we have multiple choice, our answer should be right here, and it is. It's D. Again, pretty simple stuff. All we're doing is plugging into an equation based on the information that we got from the problem. All right. Now here's where we get a little more complicated. I'm going to go ahead and write the form again so that we see that, because that's going to help us be able to understand what I'm about to explain to you. So now we have Y equals C times 1 plus R to the T power. Okay, again, that's that exponential growth and decay form. So now it's asking us, using the formula for exponential growth and decay, what would the value of R be if you were going to double? So if I wanted to double something, that means I have to do my rate. Well, let's think about this. If I have 1 penny, okay, how do I double that? Well, I have to add 1 full penny to it, right? And then I get 2. So if I double this, my R needs to be 1, right? Okay, what if I want to triple it? So if I have 1 penny and I want to triple 1 penny, I have to add what to it? How do I get 3 pennies? Well, I have to add 2, so R would be 2. So to turn this in from 1 to 2, I've got to add 1, that's doubling it. To turn this in from 1 to 3, I've got to add 2 to it. So that's how we double and triple something using this formula. You add 1 or 2. Okay, if I want half a penny, okay, I can't add a half, right? Because if I add a half, what's going to happen? I'm going to have 1.5. So I have to actually subtract, so I have a negative 0.5, or negative 1/2. So that's kind of one of those things. It's kind of hard to rationalize in your own head, but it is. It makes sense if you're thinking about 1 penny or 1 object, and then you're trying to double it, you add another 1 object. You're trying to triple it, you add 2 objects, or if you try to cut it in half, you subtract a half, right? So there's our setup for those. Okay, now based on what we just learned, we're going to need to put that into our play right here. It says, now use those values to write an equation if you had a population of 500 and it doubled. So if I wanted to double that population of 500, I would write y equals, C becomes my 500, and then my rate, my R is going to change, and then T is going to stay T. So I'm going to have C equals, so y equals 500 times 1, if I want to double it, plus 1 to the T power, or y equals 500 times 2 to the T power. Okay. If I wanted to triple it, I would do y equals 500 times 1 plus 2 to the T power, or y equals 500 times 3 to the T power. And again, if I want to decrease it by half, I would do y equals 500 times 1 minus 1/2 to the T power, or y equals 500 times half to the T power. Okay. As we move along here, we're going to go ahead and omit example 4. So you don't have to worry about that, so we can omit this. And let's go ahead and jump into our last example. I will say this, omitting 4 isn't necessarily a blessing, because our last example is probably the most complicated. We're talking about compound interest formula, which compound interest formula, again, is relatively simple as far as the fact that you're just plugging in information that you get from the problem. However, sometimes it's hard to determine the end value, and that's what confuses students often. If it says twice a year, the end value becomes 2. If it says annually, the end value is 1, and so on and so forth. Hopefully we'll kind of come across those as we see them. So if we're talking about the compound interest formula, let's go ahead and you see that A is the final amount, very similar to our exponential growth and decay, because it is a variation of growth and decay. And then P is our principal, or our initial amount. In the finance world, you call your initial amount the principal, the money you start with. Then, of course, you have your 1 plus. R now is your interest rate in decimal form. Again, that's another thing that will come up. In a percentage, you have to turn it into a decimal in order to use it, because we don't ever work with anything in math as a percentage. And then your N is the number of times it is compounded per year. Okay, so if it's compounded annually per year, it's 1 time per year. If it's twice a year, it's 2 times per year, and so on and so forth. Okay, and then it's raised to N times T power. So make sure you follow order of operations here, and T is your number of years. So let's go ahead and just jump right into this problem. Got a lot of information, so let's go ahead and highlight as we go. So it says, when Jingmei was born, her grandparents invested $1,000. So what do you think $1,000 is? Well, it's the investment, so it's the initial amount, so that's our P. It was in a fixed rate savings account at a rate of 7%. That's pretty simple. It tells you what the rate is. So we know that R is equal to 7%. If we change this to a decimal form and move this 2 spots to the left, and it equals 0.07. Okay? It's compounded annually. So the number of times it's compounded, well, it's compounded once per year, so 1 time. Okay? And then it says the money will go to Jingmei when she turns 18 to help her with her college expenses. What amount of money will she receive from the investment? So 18 is important because that's going to give us our time frame. So T, if it was from when she was born until she was 18, T is going to equal 18 years. So now we have our interest. Let's go ahead and find out how much money she's going to get after she turns 18. So we said our interest formula is this right here. So I'm not going to rewrite that. Save us a little space. But P is 1,000 times 1 plus my R, we said is 0.07 because we already converted it from a percent to a decimal, divided by N, the number of times it's compounded. It's compounded annually, so n is equal to 1. Okay, all that raised to the n times t power, so n is 1 times the t is 18. Let's go ahead and simplify. So I have a equals 1,000 times 1 plus 0.07, because 0.07 over 1 is 0.07. 1 times 18 is 18, so 1 plus 0.07 to the 18th power. So a equals 1,000. Continue to simplify. Work inside those parentheses. 1 plus 0.07 is 1.07 raised to the 18th power. Now, make sure you do the order of operations first, meaning that I'm going to do this part first, the exponent part. Before I multiply 1,000 times 1.07, I'm going to multiply the exponent. I'm going to do the exponent first. So, 1.07 to the 18th power comes out to be roughly a equals 1,000 times 3.380. And I continue to simplify. 1,000 times 3.380. All I got to do is move the decimal spot 3 places here, and it gives me 3380. Okay, and there's some change there. That's not an exact figure. That's approximately 3380, but that'll be her money when she turns 18. So, not the greatest investment. They invested $1,000, and she made $23.80 off of that. So, at the end of the day, she ends up with 3,000. If you can't see that, she ends up with $3,080. All right, that's pretty much it. That's growth and decay. The more specific uses of growth and decay. Again, we talked about growth and decay already as far as what it looks like. This is actual more application problems that you'll see them, where you'll see them, and how you use them. Okay. If you have any questions, come see me tomorrow morning in tutoring. Other than that, have a good night.